that box of metal iron shavings. And what you can see in this picture is what I saw. Those iron filings line up across that magnetic field. So here's a field where you have a positive and negative pole, and those iron filings are lining up in this interesting, really cool, artistic looking pattern. This is essentially the same principle that the soil water content sensors are using. Down here at the bottom, I'm showing, this is just, again, an electromagnetic with a positive and negative pole. And when you create that electromagnetic field, you create a field where electrons will tend to line up in an essential pattern like this. In the one on the left, I'm showing where you had like a vacuum, no material between those poles. But in this diagram, let's put water in between those poles. In this case, the electromagnetic field is affected by the material that's in between those two electromagnetic poles. The material that we have in between those poles has a property called a dielectric constant. And if we know the dielectric constant of the material and we know the strength of the electromagnetic field, we can deduce things. And in the case of soil water, we can determine the amount of water in that sensor. And one other picture I put on the screen, if you've done any circuit building ever, maybe you had a electric kit when you were younger. This is a capacitor. And a capacitor takes advantage of this exact same principle to store energy inside that component. So sometimes these sensors, soil sensors, are called capacitance sensors because essentially they turn the soil into a capacitor. Now this diagram, I'm just showing you when you put a sensor into the soil with those two needles that are acting like the positive and negative poles on that electromagnetic field, the material between those sensors is everything in the soil. So you've got minerals, organic matter, there's some air, and there's some water. But if you look at this scale, the dielectric constant of all of these materials is very low relative to liquid water. So that's the way the physics basically of a capacitance sensor is it takes advantage of the fact that liquid water has a very high dielectric constant compared to the other material. Now, if you're thinking ahead and you notice that ice has also a very low dielectric, these capacitance sensors in the soil fail to measure water content when it freezes. So if you've got a water sensor in the ground, as soon as that water turns from liquid to solid, the reading will change and make it look like your soil dried out, when really the water just changed phases. So the same kind of principle, this is just showing you if you took this sensor, this one's made by Meter Group, you got those two needles, it creates an electrostatic field. If you were to look at that field from the tip of the sensors, you would see the water, these are water molecules, that's H2O that you're looking at. Those are the charge storing elements in the soil. So that's what allows this sensor across an electromagnetic field to make that reading. So again, you might hear them called capacitance probes because they are measuring the charge storing ability in the soil just like a capacitance would. You might also hear them called frequency domain sensors. In either case, whatever you call them, this is what they're doing. They're measuring the charge storing capacity. They have to be calibrated against water content. And you'll see a variety of sensors and how they look. Some look kind of like a ruler, needles. This is a profiling type where there are rings that are inserted. But they're all capacitance type probes. Now there's one other type of water content sensor that still uses this electric measurement. These are called time domain sensors, or you might hear them referred to as TDR. And a quick explanation of how these work. They're a little different in that they measure time. The basic functions or features of a TDR sensor is a pulse generator and an oscilloscope that measures the reflection of this pulse. So what happens is the equipment, like the one you see here, here's one by Campbell Scientific, it generates a pulse and sends it down a cable. And at the end of the cable, you'll actually have the sensor that's in the soil. there is a reflectance of that pulse back to this oscilloscope. So the reason these are called TDR is they're not measuring capacitance, they're measuring time. They have to have a pretty detailed sensor in here, and it's making a plot of the reflection of that pulse of electricity over time. So that pulse goes down, hits either the beginning or end of the sensor, and this is the beginning reflection and the end reflection. It's measuring the time difference between those. It has to be a pretty sensitive sensor, so these tend to be pretty accurate but pretty expensive sensors. So quickly, I'm just still talking about sensors that measure water content. You have either capacitance or TDR type. Here's some comparisons. The capacitance, I say lower cost, they're lower cost than TDR sensors. They tend to still be, you know, on the cheap end, you might be paying $80 a sensor. So they're less than TDR, but they're still not cheap. Little lower power use. But one of the problems with these capacitance type sensors is that they're sensitive to salinity, temperature changes, and they're really sensitive to air gaps along those needles when you insert them. Each of these sensors needs to be calibrated for a specific soil type, and they have kind of a limited, they don't measure, you know, a big area of soil. They're just measuring the water content right along those needles. Compared to TDR, these cost more, they use more power, but they're much more precise. You get a more precision. So I'd buy this sensor if you're just looking for general trends. If you want to be highly precise, you might want to go with the TDR. These are more robust. You don't have to calibrate for different soil types, and they're less sensitive to temperature and salinity. One final thing about these, though, because you're measuring the time of reflectance, you can't have an infinitely long cable. So there are some cable length restrictions for those. So I'm going to pause here for a second. I'm going to talk next about water potential, but I just kind of gave a physics overview of electromagnetic sensors that measure water content. Any questions before I jump on, before I move forward?
Just a quick one, Doc. When you said the cost difference, what are the TDR compared to general cost compared to the other ones?
So if I understood the question, just kind of, hey, what am I going to expect to pay if I'm looking for these different types of sensors? First of all, when I said the price of a sensor was about $80 for capacitance, you can find some a little less and some quite a bit more than that. But that's just the sensor. You also have to have some kind of device to read the sensor. So I'll show you some of those in a minute. But a data logger or some kind of a reader if you're going out and doing it handheld. So in my experience, you can easily spend $2,000 to $3,000 to instrument a field with a handful of sensors. If you're doing multiple depths in a field and some kind of logging device. Okay. Then you also need to figure out, are you going to pay to have telemetry so you can download the sensors from your laptop or your phone, or send somebody out to measure them? So again, capacitance, you're going to be lower cost, but you might, if you're putting out, you know, sensors across depth, let's say you put 4 or 5 sensors in across depth, you're looking at anywhere from $50 to $100 a sensor, plus another possibly $400 or $500 for the logger and the telemetry. The picture I showed of the TDR, that Campbell Scientific one right here, I think this thing is in the thousands of dollars category. But this tends to be one that's used for more precise applications and research. I don't know, what I found basically is that there's a wide spectrum of costs, and others of you may want to comment too on what you've spent for sensors.
Thank you.
Anybody want to jump in with your experience on costs on sensors before I move ahead?
Yeah, the capacitive sensors are getting produced quite a bit via like open source hardware, and the cost on those has come down quite a bit. from different suppliers. So you can get those for, about $20 to $30 a piece probably. And then, in terms of the micro or how you read it, if you have a data logger or whatever, using a microcontroller such as an Arduino or Raspberry Pi or some of the other devices that are out there these days really brings down the cost on an individual basis. So, I think you could put, a station in with 5 depths for, under $200 total if you wanted to use the open source stuff.
That's great. I'm super glad that you brought that up, because there really has been some great development. And if you're handy and you like to, do some little basic programming, or even you can find online ways to construct some little sensors, in fact. So those costs that I was mentioning are kind of commercial producers of sensors, but there are some alternatives out there that are looking good, and even some development to where we might be able to get to single season applications of sensors that you deploy and don't necessarily have to go out and recover because of the cost. So
yeah, I've actually got, through the CSU crops testing program, have deployed quite a few single-use sensors essentially, and I just abandoned the deep ones and try and recover the ones that I've got at, right at the top in the first 5 inches, and maybe the one that is down at about 8 inches as well, if I can get to it. But if I can't, I just abandon them because the cost is pretty low.
just out of curiosity, are they capable of wireless data collection, or are you still having to be wired to those?
They're wired still, but the logger that I have has an embedded cell modem, so we do have telemetry on there for actually really cheap compared to some of the name brands out there.
Yeah, thank you so much for adding that in. And again, I'm looking to not too far in the future where I think we can use, a phone and Bluetooth essentially to collect data. I don't think we're quite there yet, but
I think, to be honest, I think we are in terms of Bluetooth, and Bluetooth range of 50 feet or so. You could do that, or like I said, having an embedded sensor, so it just goes all into the cloud or embedded modem, so it's just connected to a cell tower for relatively cheaply.
great discussion. Thank you.
Well, the biggest challenge I have had with soil moisture sensors is maintaining good soil contact in soils that shrink and swell.
Yeah, I couldn't agree more. The install is a really critical stage for any type of these sensors that you're using, and that contact is absolutely critical for almost every type of sensor. I've actually struggled myself with the sleeve type sensors. I know some people like them, but those I tend to have even a more difficult time getting that good connection with. Okay, I'm going to talk next about the second class of sensors that measure soil water potential rather than water content. And again, I'm going to take a few minutes and just kind of give a little background on what they measure and how they make the measurement. And then we can talk about these. And then I've got some case studies of how I've been able to apply these type of sensors. So soil water potential, it's a measurement of energy status of the water. It doesn't tell you how much water is in the soil itself, but rather it tells you the energy level at which the water is retained. So if you look at the image I've got here on the screen, this is zoomed in to the particle size level of a sand soil on the left and a silty soil on the right. What I want you to notice is the film of water that's encircling each of those particles is roughly the same size, the thickness of the film of water. In this hypothetical example, both of these soils would be at a water potential of -10 kPa or kilopascal. So again, right off the bat, you're like, what is that even measuring? It's measuring the thickness of the water films, or how tightly that water is held at the surface of the particles. I hope you could see that these two soils that are illustrated here would have very different water content. The one on the left, I don't have the number, but I'm guessing if you just said, hey, what percent of that space in that circle is occupied by water, it's going to be down around 10% somewhere, probably by my eye. And on the right, you may be up at like 30 or so percent or even higher. So these two soils at the same water potential have different water content. The value of understanding water potential is that essentially the plants sense the energy status of the water. The amount of work that it takes to extract water from the soil relates to the water potential. Another way I might illustrate that is just this graphic is showing a single pore within the soil and the surfaces of the mineral particles that are there. And when there's a thin film of water, very thin, this would be an air dry soil, that water potential is highly negative, negative 31,000 kilopascals. You essentially can't drive that water off. You'd have to put that in an oven to get that water to evaporate. It's held very tightly. As that soil gets wetter, the thickness of that film on that surface gets bigger. The water potential here, minus 1,500 kPa. This is, if you're familiar with it, is what we'd refer to as the wilting point. And then a much thicker film, we're filling the air space in that pore with water. Now we're at minus 33 kPa, that's the field capacity. And when that pore is completely filled, we're essentially at saturation. We get very close to zero. In other words, it takes almost no energy for the plant or for gravity to drain the water out of that pore. So I hope that little graphic kind of helps you read what are we talking about when we talk about water potential. The bigger numbers mean the water films are thinner and harder to extract. One of the sensors that has been around forever that measures water potential is the tensiometer. And it's, in my experience, very impractical sensor, but I like to use it simply as a demonstration of the concept of water potential. And I'm actually going to stop sharing and so you can actually see my screen a little bit. I've got a tensiometer here. If I can figure out how to hold it in the camera. So the tensiometer is essentially a large tube, like a big straw. And at the tip of the tube is a porous ceramic cup. Water can flow through in and out of that porous ceramic at the tip. And then at the other end, there's a cap, which can be removed. And essentially this cap functions like when you put your finger on the top of a straw and create a vacuum inside that. You can remove this cap, fill the tensiometer with water, and then put the cap back on. When you have this tube filled with water, when water flows out of the ceramic into the soil, the cap at the top is keeping a vacuum. And so the gauge essentially measures the strength of the suction or the vacuum on the tube. And so I'm actually going to unscrew the ceramic tip and I'm going to suck on this tube and you'll see that the gauge is responding to that vacuum. So in a soil setting, you go back to sharing my screen now. In a soil setting, it's the soil in equilibrium with the ceramic tip that pulls the water out of the tensiometer and creates the suction on the gauge. And again, I am not advocating for the use of a tensiometer here. And I've listed some of the reasons why. That they only measure water potential in the wet range. Once you get below about minus 80, or a few of them might get you a little beyond that, the water column breaks, you get bubbles and they don't work. So they're not very good on the drier side. They're really tough to install and maintain and kind of slow to equilibrate. Some people are good at them, but I think there's easier sensors to use. I just put it in the presentation because I think it helps you get your head around the idea of how a suction measurement or an energy scale relates to water in the soil. What's more common for measuring water potential are, again, taking advantage of an indirect electrical measurement. In this case, it's not capacitance, but resistance that is measured. The key to water potential sensors is that there's some kind of a ceramic or porous media. So if you, this is probably the most common one being used, I think right now. It's made by Watermark. It's a sensor that has this porous material enclosed inside the sensor. This has to be in close physical contact with the soil, and water, as the soil gets wet, water will flow into this porous material, and as the soil gets dry, it'll suck water out. So the sensor itself is getting wet or dry in the soil, and the leads, the electric leads, measure the resistance of electricity across that reading. So that's calibrated. The sensor itself is calibrated to electrical resistance at different water contents, but its water potential could be measured with some kind of a electrical reading and related to what's in the soil. Okay, so yeah, maybe before my example, any basic questions on what's the difference between water content and water potential sensors and why we might want to use it? I think I'll demonstrate that with my example, but let me open up for any input, comments, or questions about water potential sensors. And it doesn't surprise me that nobody's saying anything, I guess, because I think they're much less commonly used. Anybody out there that's used a tensiometer? All right, well, I'm going to go ahead and show you why I like the idea of using a water potential sensor. And I'm going to start with a non-agricultural example. I'm going to talk about a little demonstration I did here on my campus at BYU in Provo. Here from this picture, you can see one of the reasons I liked to move here. It's a beautiful town, the big Y on the mountain for our university. But this is the demonstration site. It looks like nothing too exotic, but Brigham Young University has a real turf football stadium. And at our research farm, they built a model essentially of the layered soil structure that's in the stadium. Anytime they want to test a different product or something, they don't want to mess up at the stadium, so they do it here. I asked them if I could demonstrate the use of soil water sensors for measuring water content at this little demonstration site, and they allowed me to. I installed here's the logger. I have buried cables going out into the middle of this turf. The installation looked like this. I put a water content sensor, so this GS3 is water content. I put one at 3 different depths. And then I also put water potential sensors like this one at the top 2 depths, so they're fairly shallow, 2.5 and 6 inches down. And then I just tracked those over time. So this is a busy figure, and I'm going to walk you through it, and it's kind of a fun story if you can stay awake for it. When I first put those sensors in, it took a little time for everything to get working. But if you look at this section of the data here that I've labeled with the letter A, there are 4 lines, 2 for the water content sensors, those are right here, and 2 for the water potential sensors, which are actually pegged up here at the top. To read the water content sensors, you read it off the left axis. So volumetric water content from 0 to 50%. And to read the water potential sensors, they're on the right-hand side y-axis in water potential kilopascals. So think about it with me for a minute. What's happening in this turf grass during this time period? What you see, if you can see my mouse, can you see my mouse when I'm tracing this here on the screen? Or?
Yes, we can see.
Yes.
Okay, good. So if you trace my mouse here or my tracker, right here, if we start, you see the water contents going down, and then there's an irrigation event. And then it goes down a little and irrigation, go down. And if you look down here at this time scale in June, essentially the BYU grounds people had the sprinkler set to come on every day. So you can see wetting, drying, over and over. That's that sawtooth motion going on right there. Anybody want to tell me what's good or bad about what's going on during this time period right here? Just by what you're seeing on this screen, what's your interpretation?
The challenge I would see, Neil, is that you're not doing anything for root system. All you're doing is feeding it right off the top of the soil. So you're going to be really prone to any stress events if they don't get water to it on a timely fashion. Also looks to me like there's a little bit of a diurnal cycle there. Daytime, nighttime going on.
Yeah, that's a good observation. And these sensors, as I mentioned earlier, they do have a little temperature sensitivity. And so sometimes you'll see them doing this diurnal pattern. But Dave, you're exactly right. There's, if you're just looking at the water content sensors, and essentially when I showed this to the grounds people, they're like, oh yeah, I can see our irrigation's working. They actually thought this was good. I had to teach them, wait a minute, look at the water potential sensors. So your eye doesn't even notice them because they're pegged up here at the top. These water potential sensors are essentially at 0. And remember what 0 means is that the pores are completely filled with water. This is a fairly coarse textured soil. This is really, I'm jumping ahead, but to be in its ideal water content, it's probably down here in the 12 to 15% water range. This thing is saturated. There's no air in there. And I took this and I explained it and showed the grounds manager, said, you're just putting way too much water on it. And sadly, turf grass is often managed this way. It's just a continuous flushing of water going through, and that can create a lot of problems. So I made a deal with them. I said, look, let me have control of the sprinklers. And this time scale B right here was Neil Hansen managing the irrigation on this turf grass. And I'm not a turf specialist by any means. They said, okay, we'll give you a little time. Go ahead, take it. I turned off the sprinklers. And I said, I'm just going to go manual with this. I'm just going to turn them on when I see it. And I just started watching the water potential sensors up here at the top. And we essentially went more than a week, almost 10 days before this water potential sensor started to drop down. One thing that was scary for me, I realized pretty quickly, is it drops fast. These sandy soils, and many of you that have worked with them, yeah, it'll go from fine to excessively dry really quick. But I watched it, and when it got down here, I was shooting for about -300, which is what, again, I'm not a turf specialist, but I had read Kentucky Blue can go to -500 pretty well without really too much stress. So I decided I'll take a buffer. I'll try and hit about 300 and then turn the sprinklers on. And this is really fun. Look at that. Over a period from early July till almost the end of August, we irrigated like 5 or 6 times total. And the grass looked fantastic. I had these guys eating out of my hands. They're like, you got to be kidding me. They were looking up the prices of sensors for the rest of campus. And now I'm going to tell you the sad part of this story.
That's
Time C on this graph. If you look at the date, it's the end of August. The other half of my job is teaching. I do research and I do teaching. And at the end of August, I got crazy stressed out and dizzy getting my classes ready. And I stopped looking at the sensors as carefully as I should have. And on the 30th of August, something like that, this thing tanked. It went down to almost -1,000 before I caught it. Of course, I ran out there, turned the sprinklers. I made the mistake. I just started watering like crazy. Like I hoped I didn't kill it. And it actually came back. It did okay. And then I actually had another even worse time scale D. I got below 1,500, which is the wilting point, and I killed the turf. And the turf was replaceable, but sadly, what I really lost was my relationship with BYU Grounds. And they decided they didn't want to buy sensors all over campus. So I'm still trying to rebuild that relationship. I think I showed them the principle that these sensors, and really including a water potential sensor, has value in understanding what's going on and in tracking irrigation. The problem in this situation was the human error, not the sensor error. Okay, so that's my first example of why and again, I might come back and just say, if you just had the water potential the water content sensors in here and you didn't know much about the soil properties, you could easily misinterpret where you are on that wetness scale. It wasn't until I put water potential in here that I was able to demonstrate, yeah, we need to get this water content down to about 12 to 15% to be in the really ideal range for managing the water on that soil. Okay, the second example I'm going to give is an irrigated potato field. This is up by Grace, Idaho, and I'm going to talk about that for the last few minutes of my talk. I'm working with a grower in Idaho. This guy is super interested in technology. He does all his field scouting with drones, and so he was a good person to work with when it came to installing sensors. The long and short of this story is we took about a 50-acre, half of a center pivot field, and we installed 5 nests of sensors, and there was no variable rate irrigation, just irrigated uniformly. I just wanted to show him, let's look and see what the variability of soil water potential is in this field. So there you can see one of the sensor networks that we installed. I don't want to candy coat the installation of these sensors. I mean, I take a team of students with me, and it takes us a full day to put in 5 sets of sensors in this field. So one thing about sensors is they do take time, and they take energy, and they have to be maintained. So here's the story at the end of the growing season. So this time scale is June through end of August. I just let him irrigate. He irrigated his field as he normally would. This is showing water potential, again, getting drier as you go down all the way to the wilting point. And the grower was pretty shocked when I showed him the results. There were 3 of the 6 sensor sites that we put in that were, I would say, pretty ideal. They were maintained up here in that wet range. They never got too dry. The 3 of our sites really started drying by middle of July and never really caught up. These are sensors, by the way, at the surface. There were roots below this, and we had sensors a little deeper than this too that didn't get this dry. But I just want to show, wow, in one field, fairly uniform soil type, there's a lot of variation going on out there. Dave, you can see that diurnal variation still going on, but the basic trend on these sites is getting dry. I had the grower just say, hey, go to your yield monitor. He has a yield monitor for potato on his potato digger, which is pretty unique. He's a techie guy. And sure enough, those 3 sites, 9, 10, and 12 at the top here in yellow, had significantly lower potato yields. So I think we were able to convince him that uniform irrigation is not necessarily uniform soil water stress in the field. So I'm going to summarize this part of my talk, and I just have one little more piece on VRI that I want to talk about. I'll just give you my opinion on sensors. I love them, obviously, but that's kind of my bias. I like to have real-time dynamics of water content. I like to be able to track things like stress and rooting depth. And as far as whether I like content or potential sensors, they both have their advantages. But one thing about the water potential is it's really telling you what the plant feels rather than just the amount of water in the soil. But again, there are struggles. They're not perfect. They measure they're only measuring water content right around that sensor, not on the whole field. As we talked about earlier, you got to have really good water soil sensor contact to make them work. And when you install them, you can also get another problem where your installation is creating a disturbance in the soil, or the cables themselves create these preferential flow paths. So it takes a little work to figure out how to get these things to work right. And then costs and maintenance and all those things. So I'm going to end up with one example of the use of sensors in a VRI system. It's the same grower that I told you about. And he and I have been working together for about 7 years. He actually liked what we showed him with that variability and invested in a pretty nice VRI package. But the reason he did that was not just because of what I showed him on this half of the pivot. In the foreground, you're going to see what I think is the only center pivot irrigated golf course that I've ever heard of. This landowner, he and his dad are golfers, and they wanted a golf course, and they built one. So the pivot, half the circle is the golf course in the foreground, and the other half is that same field where I was showing you the potato results earlier. The VRI makes perfect sense on the golf course because he can shut water off on these out of bounds areas. He can irrigate differently on the greens. It's a really nice system. For him, the VRI makes sense on the ag field too. You can't see them too well, but these dark spots back here in the back of the field, these are rock outcroppings. This is a volcanic soil, and there's areas that he can't farm. And so he's able to turn the sprinklers off on those areas. And even that bit of water savings he thinks is worth his investment for the VRI. What we did then is we went crazy like researchers do and said, hey, what could you do with the VRI on the farm side of this field? If you're interested in looking up that golf course, it's called Caribou Highlands. And there's not a tree on the place because you can't get the sprinkler through a tree. But the greens are really good. He has some really nice greens there. This is the ag side of that field. The points on the field is what I sent my students out to collect soil water content multiple times during the year. This is something I'd never recommend for anything other than research. This is how we're taking the soil samples. We use this modified post hole driver to get our core in. Then the hard part of the job is pulling that out of the ground. Then the students will take that core and chop it up in pieces. So we're able to get water content at multiple depths throughout the year. Again, I'm just trying to say, what should you do with your VRI from a research standpoint? Here's what you'll see. That field, the farmer himself describes it as highly uniform, but we found things like field capacity vary, not hugely, but some areas of the field, they hold more water than other areas. So that might be one way you'd set up your VRI pattern. We also looked at historic yield maps that he gave us, and you can see areas of the field on the left here that just historically yield a little higher. We took a combination of historic yield, soil, and ET patterns and generated a 5-zone irrigation map. So this is the VRI map that we recommended he try. Again, I've just put our research points on top of that. We put a soil moisture sensor station in each zone, and then this for a year of winter wheat, we tracked the irrigation. Every time he wanted to irrigate, we would look at the sensor values. I could do that from Provo, even though I'm 4 hours away from him. I'd look up the sensors. I'd compare the current reading with the field capacity value for that individual site and make an irrigation recommendation to him. So this is good VRI. It's using soil sensors and some basic information to create those zones. Here's what we came up with. These lines I'm drawing in here are the irrigation over a growing season for each zone compared to what he normally would have done for that field. The dotted line shows actually the total irrigation for the zone that required the most water hit about the same amount of water, but all of the other zones were water saving zones. VRI saved water in 4 of those 5 zones. And when you look at the field average, the water savings, I don't know, it's not huge. It's roughly 10 to 12. So a 2-inch water savings on that field. What he told us was it was more than the water savings. He actually had a lot more flexibility and the timing of running his pivot, and he was able to manage the golf course better by knowing what he was up against. Looking at the sensors, he could decide, oh, I can go ahead and irrigate the golf course because the sensors are still in a safe place. So in kind of summarizing here, the question is, do you think VRI is worth it? You got to invest in the VRI as well as the sensors in this case. So a lot of cost. Are they worth the benefits of, and again, I'm giving you his words. He liked it because of the reduced pumping and water costs. He thinks he's was over irrigating before, so he's reducing leaching and fertilizer loss, and then that flexibility there. And I'm going to end with this slide. I just thought you might find it interesting. We were still sending students out and measuring water content in all the other points, and I just compared it to what the sensor measured. So this is one day. If you look at this one that I've drawn up here, the sensor actually hit the average of all the points in that range pretty well, but there's quite a bit of variability even within a zone. Not every, the X is the sensor. Not everyone was perfect, but the sensor in that zone did a pretty decent job of representing the variation of water within the zone. All right, I'm tired. I've been talking fast and you're tired of listening, so I'll stop there. I don't know if there's time, Wilma, for any questions, but I'm willing to take them if there is.
Yeah, we have plenty of time for questions or for more discussion. Well, my microphone was mute, so yes, we have time for questions or any discussion.
And I'd love to hear input from you guys too, what you think about this idea of VRI and sensors. But yeah, Brian, go ahead. You had a question?
Yeah, we've used some AquaSpy sensors down in our area, mainly to satisfy the NRCS requirements, but they seem to really work well. Have you ever tried those? They're a simple column installation and they go straight to the cloud, so you can pull them off the computer and stuff.
Yeah, I haven't used them a lot, but I've worked with people that have, and I've heard positive feedback on them.
And
again,
as I
it's a
understand,
water,
they'd probably be the water potential. I was just looking up on their website while you were talking, but I think that's what they do.
I think not. Again, I better defer, but I think a water, they're a capacitance sensor that's measuring water content.
Oh, okay, okay.
Right, you're
I might
getting a
have read
number
that.
back that's a percentage base, like it's giving you a percent, not a KPA type reading.
Correct. Yeah, and
Yeah.
the nice thing about them, they're already calibrated and they seem to work fairly well. Unfortunately, we're such a limited water situation. They don't help us a whole lot because we're usually in the close to the deficit area, but I like how they work. And I know I had a guy growing grass and he realized, oh, that's why this field's not growing too well. I'm a little short on water. It's like, well, yeah, that makes sense.
Yeah, and I think that type of install works pretty good in a perennial situation where you don't have to dig them up all the time, because they install into kind of a sleeve, right?
Yeah, they're already in a PVC column. They got sensors every 4 inches. And
Yeah.
so you just install the whole thing in a pack. You know, they've got a certain way you install them, but it really doesn't take too long at all. And we've had really good luck with them once we've got them installed. So been pleased with them.
So yeah, I think they're a high-end capacitance type sensor, and they work pretty well. They have the same vulnerabilities as any capacitance sensor, and yeah, they do. You have to have some kind of a translation for that electrical measurement to water content, but they've worked out a lot of details, and I think they have some temperature sensors in them, so they're compensating for the temperature effect.
Yep, they do. So, but thank you. It was good talk.
There are some comments on the chat that you wanna.
Yeah, I see those, and both Zach and Joel are confirming that they're a capacitance type water content sensor. And again, yeah, you on the dry side, as long you're not going to have the problem that I was having in my turf example, where they didn't know that they were too wet until we put the water potential sensor in there. But you do know you're too dry probably in your particular application. So.
Hey, good morning. I was just curious if the yield data evened out after the variable rate irrigation was applied.
Yeah, I'm glad you asked. In fact, I'll show you that. because I probably should have shown that. Very interesting part of the story. Where is that? Don't tell me I took it. Here it is. So this is super interesting. The yield still shows that higher yield production on that left side of the field. It always produced more, and even under VRI, the yield was not super water dependent is what we determined. And that's what we were hoping. We were hoping that those drier areas, we would bring the yield up. What we conclude is that it's a lot more complicated than just the water. It's fertility and you know, a lot of factors that are affecting yield. So I think if you're hoping that VRI will give you a great uniform yield, you may not get that. I think that what you get is more precise water application and a little bit better management of water. What I can say is with that 2 inches of water savings, the grower felt like the yield was better than the historic average of that field relative to his neighboring fields that were not in VRI. So he was happy. He felt like we didn't drop the yield any when we saved the water, and maybe even brought it up a little bit, but the spatial variability and the yield did not go away. Yeah, thanks for asking that. I probably should have shown that.
You know, I think that's, Neil, that's something we've got to remember on all of this variable rate stuff. We've got a background soil out there that's highly variable, no matter what the soil survey says. And the best we can do is maybe maximize the yield for that soil with all this variable rate stuff. If we think we're going to uniform a field, we've got to go out there and in essence, build us a uniform soil, and that isn't going to happen. So I know the work that Raj has done in that little plot at Fort Collins is the same way, even though it's all silt loam. You know, he did a session last week. So yeah, when you start looking at the differences in those silt loams across even that 40-acre patch, there's a lot of variability. So the best we can do is hope for economic maximum given the background conditions that we have, soils and maybe some other conditions too.
Yep, I agree completely. And you know, one of the challenges of VRI is what should you use to create your zones? The field that I was showing you, if you look at the web soil survey or a soil map, it has just one soil type for the whole field. And I have a graduate student I actually asked to do this. It's kind of funny. I said, take that field and have, you know, some child, get a 4-year-old child and a crayon and ask him to make 5 zones on that field for you. Totally random, right? I'm pretty convinced that if you were to do something like that, you're still going to manage your water better if you were managing just 5 smaller fields rather than one big field. So I think in some ways, just localizing the management would help. Of course, I hope we can do better than that we can use yield history or elevation data or something like that to do better than the random dividing. But in any case, that the concept of VRI or any other variable management is that you're taking a more localized look at the needs for inputs.
Neil, I'm curious if for that experimental field that you did, if the water data that you got or the moisture data that you got matched up with any elevation data that you had.
Yeah, actually, I didn't include this in my presentation, but this student I referred to is basically saying, what's the best simple data set that you have to create zones to match our observed spatial water content patterns? And the 2 variables that are most useful are elevation and slope. And so, yeah, the lower areas of the field, and this is a field with not a lot of elevation difference. I think it's less than 10 feet maybe of difference between the highest and lowest area of that whole field. But the lower areas of the field are wetter, which suggests there's a little bit of like lateral movement or subsurface flow. Even under uniform irrigation, they're just wetter down there. And so I think right now, I'd say if you were trying to delineate variable rate irrigation zones, I would use those topographic variables to do it.
And maybe for the installation of sensors where you're putting your sensors, so you make sure not all the sensors are in a low or a high area, and maybe your sensors are looking at the elevation profile. Additionally, with any, on-site knowledge about soil texture or whatever, like.
Yep, well said. I agree.
Well, if there are no more questions, I'm gonna share the QR code for the CCA to scan down.
Great presentation, Neil. Thanks for coming back to Colorado.
Thanks, Jerry. Good to hear from you.
Here's the code. We still have about 10 more minutes for the next webinar. So we can end this and move to the next one, or we can stay here and continue the good discussion.
So did you compare the soil textures on your slopes to what was reported on the soil survey? Just curious if the changes from the time that the soil survey occurred to now were greater on your steeper slopes or on your high points than in the valleys.
Yeah, that's a great question, actually. We have done soil texture on every one of those points I showed. So we've measured this field to death. I actually don't know if I've done is it off more in certain areas than others? I will say in general, none of them match well with what the soil survey reports. I don't even think they're, if I remember right, even in the same texture class. So, I suspect that the mapping of this field there was never a measurement in that field. It was expanded from similar landscape features into that field. So I generally feel like the web soil survey is an incredibly useful tool, but as we get to where we're doing more precise and localized management, we have to get local information to really understand the soils. But yeah, I don't think I have a specific answer to whether the difference between the soil survey is more in certain parts of that field. I could look at that. That's an interesting question.
Off of that, I'm curious if you know of any efforts to essentially crowdsource a better soils map with, as people are doing more and more soil sampling and geotagging those samples at different depths, even if it's not as complete of a profile as someone might do with the NRCS might do or something.
Yeah, I know that there is an effort on that with regards to fertility. I forget the name of the organization that's doing this. It is essentially a coalition of the soil testing labs. They've done some very fascinating stuff where they've done exactly what you described with fertility measurements. I don't know that data goes on to include basic soil physical properties like texture, but one of the most interesting things I saw when I read that report recently was generally across North America, there is a decline in soil phosphorus testing relative to past years. That most of our agricultural soils are actually depleting in phosphorus, which, we've been so much concerned about over application of organic materials or whatever. We focused a lot of attention on high phosphorus soils, and they're out there, but they're very patchy. And as a whole, soil phosphorus has been depleted across agricultural soil. So that's one example of that type of approach to describing soils that I think is fascinating, but I'm not aware that it's gone beyond the fertility assessments.
Thanks.
Well, thank you very much, Neil, for your presentation, and it was great to see you again.
Yep, thanks for the invitation. I enjoyed being here.